So if you watched the refraction video, you'll know that when a light wave moves from a more dense medium, here in this case glass, into a less dense medium, then the wave gets refracted away from the normal, right? So I'm just going to draw that over here very briefly. So if we have a light wave coming in, or any other type of wave, here we have our normal, and notice it's coming from the more dense, right? And then it's going to be refracted away from the normal, right? So this is your angle of incidence, and this is your angle of refraction. Can everybody see it? So it's coming from the top of the page down. It gets refracted away. Now, it gets refracted away, and so hopefully what you can see is that if I were to increase the angle of refraction, right? If I were to make this angle bigger and bigger and bigger, that as I did so, then the angle of refraction would also get bigger and bigger and bigger until at some point it can't get any bigger. Okay, and so the idea is and so eventually the angle of refraction, the angle of refraction can increase until 90 degrees. That is the most that it can be, because then it just runs along the surface of the glass, right? So the angle of refraction cannot be more than 90 degrees. And the angle of incidence at which the angle of refraction becomes 90 degrees is called the critical angle. And that is abbreviated C. So the critical angle is the angle of incidence. All right, so this angle here that causes the angle of refraction to be 90 degrees. I'm just going to abbreviate it R. So the angle of incidence is I, right? Oops, I. And so the angle of incidence at which R, which is the angle of refraction, equals 90 degrees. So let me draw what that looks like, okay? So if I have a wave coming in at a very large angle of incidence, okay, then I have my normal here. The idea is that if this angle, I, equals C, if the angle of incidence, if this is the critical angle, then this wave is going to travel right here, right along the surface of the glass. And so the angle of refraction, because remember the angle of refraction is always between the wave and the normal, here is 90 degrees. So R is 90 degrees. That is the critical angle. Okay? So if the angle of incidence is less than the critical angle, then you simply get refraction, right? Just like over here. So here we know that the angle of incidence is less than the critical angle because you get refraction, okay? At the critical angle, you still get refraction, but where the refraction is 90 degrees. So then what happens if the angle of incidence is greater than the critical angle? So if the angle of incidence is greater than the critical angle, so I'm going to put this, the wave comes in at a very large angle of incidence. So we still have, this is our normal, you still want to draw that. And this is our angle of incidence. All right, and now the angle of incidence is greater, it's bigger than the critical angle. All right, and so the angle of refraction can't be greater than 90 degrees. So instead, what happens is the wave doesn't leave the glass. It cannot leave the glass, and instead it gets reflected. So it stays within the more dense medium and it gets reflected. And the excuse me. So, and for this, the rules of reflection apply. So now this means that the angle of incidence, which is here, sorry, I didn't draw these very well, but the angle of incidence is same as the angle of reflection. And this is called total internal reflection, or TIR for short. All right, so if the angle of incidence is greater than the critical angle, then total internal reflection occurs. All right, so then the wave doesn't, and this is used a lot in optical fibers and things like that, endoscopes, so that you can basically keep a light wave within a very tiny fiber. And the idea is that you coat the fiber on the inside is made of a very hard plastic, and so it has quite a small angle, critical angle. Right. So if you want total internal reflection to occur, there are two things that need to happen. One is that the angle of incidence needs to be greater than the critical angle, and the other one is you must be trying to go from a more dense medium to a less dense medium. And of course, we have an equation to talk about the critical angle. All right, so you can determine the critical angle by this. Okay, so the sine of the critical angle is the same, is equal to 1 over n. And remember that n is the refractive index. Okay. You'll notice I haven't put any units up for this. All right, the refractive index, remember, itself is a ratio of sines, and this is a sine as well. Sines are ratios, and a ratio is a part to a part, so you don't actually have any units for this. It is simply a number. All right. And so the idea is that the denser the material, which means the higher the refractive index, okay, the smaller your critical angle is going to be. So for example, diamonds have a critical angle of, I don't know, something like 28 degrees or something like that. I can't remember exactly. You don't need to know it. But the idea is that it's very small because diamonds are very, very dense. Okay. Whereas glass is something around like 1.3, water is 1.2 something. I can't remember. And so the idea is that the more dense a medium, the smaller the critical angle will be, because you're going to get larger refraction when it tries to go to air, is the idea. All right, so that's your equation. And this is your total internal reflection.